computer science at the University of Illinois Urbana-Champaign. He did his PhD from MIT. He got his PhD from MIT with Antonio Torralba and Russ Tedrake, and he completed a postdoc collaborating with Fei Li and Jianjun Wu at Stanford. His work stands at the intersection of robotics, computer vision, and machine learning, and today he will be giving a talk titled Learning Structured World Models from and for Physical Interactions. Thanks again for joining us, and the floor is yours.
Sounds great. Really appreciate it. Thank you, Sasha, for the very kind introduction. And really excited to be here to present our work on the topic of learning structured world models from physical interactions and for the robots to do better physical interactions. And the goal of my talk today is that by the end of my talk, you'll be convinced that we should add structure to our learning systems. And with a suitable choice of structure, the system will have a much better generalizations and sample efficiency, especially for complicated physical manipulation tasks in the real world. Later, I will show examples like manipulating dough, granular pieces, as well as a lot of open world manipulation tasks. And those can all be benefited by adding structure to the learning system. In recent years, we have witnessed a tremendous amount of progress in the field of robotics. In certain, at least restricted areas, robots start to become on par or sometimes surpass human capabilities. For example, the humanoid robot built by Boston Dynamics has clearly surpassed my personal capability. Or in the self-driving domain, although we haven't really seen a massive deployment of self-driving cars everywhere in our everyday life, the field has progressed a long ways over the past few years. But what about complicated physical interactions with the environments? How far can we build robotic manipulation systems that can achieve human-level manipulation capabilities? Here are some examples of what's currently deployed in the industry for commercial uses, where the robots typically handle relatively simple objects for simple pick-and-place tasks. Yet we humans can perform much more complicated manipulation tasks. Examples like cracking eggs, spread butter on a piece of bread, making dough, and making sushi. All of these capabilities goes far beyond the reach of the current robotic systems. And I want to argue that one of the key enabling factors is our humans' intuitive model of the environment. It understands the structure of the environment and predict how the environment would change if we apply a specific action. For example, looking at the following two videos, although the manipulating objects are very different from each other, one is dough, the other is a pile of onions, we can accurately recognize the semantic and dynamics of the object within the environments, and we can predict how our actions will change the configurations of the objects, like how the dough will deform and how the onion pieces will move around. It's exactly the modeling and predictive capabilities that helps us plan our behavior in order to achieve a specific goal. Here is how the framework generally works. We have a planner in our mind. We will obtain some observations from the world, and our planner will come up with some actions to execute it in the real world to trying to achieve some specific goal. And within this kind of planner, we have this intuitive model in our minds. We can get observation and actions and imagine how the environment is going to change, how the observation, how the representation of the environment is going to change when you apply a specific actions. So this is essentially a predictive model. And in order to build such kind of predictive model, there are generally two ways of doing it. One is to learn the model from data. We can roughly categorize it as model-based reinforcement learning. The typical framework first maps the observation into a latent space Z, and then learn a dynamics model predicting the evolution of the latent space. It can directly learn from partial observation and handle systems where the underlying physical equations are unknown. There are success stories like MoveZero or controlling robots from pixels. However, most prior work assume that Z is a one-dimensional vector, which is unstructured and limited in generalization. For example, when looking at a Play-Doh or a pile of coffee beans, we're not thinking of them as a single vector. Instead, we have a good understanding about the structure within the systems, the constituting components, and the relational dependency structure. It's exactly the structured understanding of the environment that allows us to handle objects with complicated physical properties and complicated relationship between objects. Talking about the structure, The other way to build a predictive model is based on analytical physical equations, like F equals ma. This is arguably the most compact way to encode the structure and has excellent generalization. It is also extremely useful in constructing robots, constructing models for the robots like the humanoid robots or the rockets. However, such physics-based model typically relies on the assumption that full state information is available, which is often not the case for complicated physical interaction tasks, like the onion manipulation tasks. Estimating the state of each and every one of the onion pieces is hard and nearly impossible. Or for the shirt buttoning tasks, the physics-based model typically requires full state information of the clothes before it can simulate the buttoning process, whereas we humans only require some local information to accomplish this task. So both methods will have their pros and cons. The left is model learning, and on the right is structures in the model. So my research aims to bridge the gap and get the best of both worlds. That trying to learn models capture the structures of the underlying environments from physical interactions and for the robots to do better physical interactions with the environment. To make the problem a little more concrete, we aim to minimize an objective function C, defined over the observation Y and the action U. And we have to think through three most critical constraints in this optimization problem. The first one is the perception module that essentially maps the observation Y and U into some sim representation Z. And then is a dynamics module that essentially takes in the current representation Z and the action and try to predict how the Z is going to change when you apply this action U into this environment. Then is this control module that derives the control signal based on the sim representation to minimize the task objective. And if you look very closely at this problem formulation, you realize that the choice of sim representation Z has a profound impact on the design of all components throughout the entire system. So thus it is of paramount importance to think very carefully on what kind of representations we should use, and for given tasks, what kind of representations should we select to suit the specific structure of that task. And we have to think about the selection of the representations implication about the entire system's structure. I will show how a suitable choice of representation and structure can lead to better generalization and sample efficiency. I will also show how it can enable and significantly boost the robustness of the entire system. The first type of representations I want to show is the form of particles. This particle as a representation essentially represents the environment as a very fine levels of abstraction. Essentially, if you look at these images, you realize the particles are combined together to represent objects of different materials, like rigid object, deformable object, fluid, etc. And the particles essentially describe those objects' geometry, as well as the relationship between those objects. And in order to model the dynamics of the particle systems, we use graph neural network, specifically graph-based neural dynamics model. Here is just very simple illustrations of how this graph-based neural dynamics model works. Specifically, what you are seeing here would be 3 nodes and 3 directed edges. And this together would be our sim representation Z. It consists of the node set as well as the edge set. And for each directed edge in the graph, for example, going from point B to point A, we have an edge encoder that will take in the informations from the sender B and the receiver A. It will output an representation for that specific edge, EK. And then for every node inside this environment, like A here, we will aggregate all the edge representations on edges where node A is the receiver. And the aggregated information is combined with the node information on node A. It will pass through a node encoder to derive the node representation. And we can then define the loss function between the node or edge representations and the quantity we care to train the entire model. In our case, what we care would be, for example, the evolution of the environments. Hence, the loss function would be the mean squared error between the node representation and the next the state at the next time step, essentially the predicted A and the actual A in the next time step. And the parameters we're optimizing inside this model will be the parameters within this node encoder and edge encoder. And one thing to note is that we exploit the compositional nature of the systems, where the node encoder is shared among all nodes and the edge encoder is shared among all edges. Thus, a learned model can naturally generalize to systems of different sizes or even outside the training distribution, as we will show later in this talk. Here will be some like learning results. On the left will be the ground truth. On the right will be our model's open loop predictions by using this graph-based neural dynamics model. The inputs to our model will be the position and velocities of all particles of the initial frame. And our model will be able to predict how the environment is going to evolve. Here, the example shows like two fluids fall down and merging with each other. You can see the prediction is very close to the ground truth. Here's another examples where we grip deformable materials using two cuboids, which are these two cuboids are to mimic two fingers of a parallel gripper. Here's another example of shaking a box of fluid. Here we assume the container is fully actuated. Our model accurately predicts the long-term future by taking the particle state at the first frame and the subsequent actions for controlling the container's movements. Those information are put into our learned model, and our model is making open loop prediction to predict the dynamics for those fluids. As we have discussed earlier, all nodes share the same node encoder and all edges share the same edge encoder. Thus, our model can naturally generate to systems with more particles than during training. This example shows that our model can work in an environment containing 2 times more particles than during training. It is clear from the video that our model captures the wave of the fluid particle caused by the container's movements and maintains the density and incompressiveness constraints of the fluids. Okay, after we have learned the model, how can we use it for control tasks? In this work, because the learned model is a neural network, which is naturally differentiable, we can then extract gradients from the learned model using off-the-shelf packages like PyTorch or TensorFlow. We can then use gradient descent to optimize the action signals and apply model predictive control framework to account for the modeling error. More specifically, here we use the blue dots to represent the initial state of the system. The goal is to achieve the target shown in red. We could have some initial guess of the action sequence U and use the learned models to predict the evolutions of the environments, essentially the control outcome. We can then define a loss function between the predicted outcome and the target, and then backpropagate the gradients of the loss function with respect to the action sequence. We can then iteratively update the action sequence to minimize the distance between the predicted outcome and the target. So this is essentially like a shooting method, and the model may not be accurate enough. So we use model predictive control, where we only execute the first action U0. We then obtain a new state Z1 from the environment. We then re-optimize the action sequence U using gradient descent to give the model an opportunity to adjust its action sequence to account for the prediction error. And here, I want to show you that the key to the success of this method is to leverage the parallel computing power of GPUs, where we can sample hundreds or even thousands of action sequences and do gradient descent for all of them simultaneously. This allows the planned trajectory to perform some local refinements and at the same time using sampling to get around some local optimal. Here we show our model's control results. The goal here is to shake this box of fluid where the control signal will be the position of the fully actuated container. What we want to do is that when the countdown goes to 0, we want the shape of the fluid to match the target shape shown on the top left. Here will be the control process, and here's the results. And here's another examples of shaking this box of fluid, and here's the results. And we also test our methods on the manipulation of a deformable form. Here, the decision variables will be the position, orientation, and the clipping distance of this parallel gripper. And after 2 grips, the result roughly matches the target. Here's another example of gripping this deformable form into achieving the target shape, shown on the top left. And here are just some more results we have been doing in the real world, where the goal is shown on the left. In the middle, we're showing the action synthesized by our model predictive control framework. And on the right will be the manipulation results. And recently, we have also been deploying similar graph-based neural dynamics model for some more complicated manipulation tasks, like for example, manipulating this pile of granular pieces. And this is a paper recently accepted to RSS. As you can see, the same graph-based neural dynamics models can also model the dynamics, especially the change of the distribution of those granular pieces when the robot applies a specific action. And we can, using this predictive capability, to plan the robot's behavior to manipulate these object pieces into achieving some complicated target shapes. And you probably already realized the target shapes here are all the letter shapes from letter A to letter Z. This is not a trivial task if you think about it. It actually involves some non-trivial redistribution of the object pieces. And after the redistributions, you have to align the detailed geometries with the target shape in order to achieve this task. And our graph-based neural dynamics model will be able to enable this kind of capability. And to take a step back and think about how we are actually doing the real-world experiments. Specifically, for the form manipulations or the granular piece manipulation, what we are doing is essentially sim-to-real transfer. We first have a physics-based simulator, and we learn the model from informations obtained from the physics-based simulator. And in the real world, in order to apply our algorithms, we will do some perception system like 3D reconstruction or estimation of the foreground. And then we'll do some online adaptation to adapt some parameters in our learned model in order to make our model more accurate and more adaptable to the real world variations and the mismatch between the sim and the real world physics. But however, we do not have a physics-based simulator that can simulate everything around us. So we are asking the question, can we remove the dependency on a physics-based simulator and directly learn the model from real data, ideally for far more complicated tasks? And I'm from China. So given that I've already worked on the manipulation of elastoplastic objects, I thought, why not try to make some dumplings? So let's see how we can proceed using real data without relying on physics-based simulators. And dumpling making is actually an extremely long horizon task, which requires the use of diverse tools and manipulation of deformable objects like those with complicated dynamics, as well as the interactions between the dumplings and the robot n factor. Before talking about how our robots accomplish this task, let's take a look at how our humans will approach it first. To make a perfect dumpling, first we have to blend the flour, water, salt, and other ingredients together. Then we will knead the dough until it has a smooth and spherical texture. Next, the dough is deformed into some elongate shape. And then we'll segment the dough into smaller portions using a knife. And then we'll be able to using a rolling pin and our hands to flatten those portions into dumpling skins or dumpling wrappers. It's then time to fill them with the chosen ingredients, the dumpling fillings. And then after some kneadings, the dumplings are ready for boiling. And this, if you look at this process, you realize this is an extremely complicated process if you really want to ask a robot to do all of those tasks. We humans highly rely on our hands as well as different type of tools like knife and rolling pins to make these dumplings. So how about constructing a robot systems that can use these diverse tools to make these dumplings? Those are the tools we are using inside this environment. So inspired by our everyday tools, we create a toolkit for robot arms featuring 15 different 3D printed tools, including, for example, grippers, rollers, pressers, cutters, spatulas, and, for example, hooks. And similar how we humans follow certain rules within a constrained action space when using a specific tools. We also simplify the tool action space for the robots. There are 9 tools with at least 3 degrees of freedom, where you can move around as well as like open and close the gripper. And we also have 4 tools with 2 degrees of freedoms and 1 tools with some pre-coded primitives. And we also develop systems for the seamless switching between those tools. We put these tools on the 3D printed racks, highlighted by the by the white dashed lines on the left image. And here the yellow ellipses indicate the 4 RGBD cameras we use to observe the environments. And then the red rectangle delineates the robot's arm's workspace. And now let's see how our system works in action. So here will be how the robot works in making a dumpling using these 15 different kind of tools. What's interesting about this video is that there will be a human constantly perturbing the robots. We will show the robustness of our robot cook framework by allowing these external human perturbations during the real world and real-time execution. First, after the robot cuts the dough, the human puts the excess dough back. The robot has to cut again to have the dough in the right volume. Then the robot will choose to pinch the dough, but the humans will also come in to grip the dough into some irregular shape. But the robots will still accurately achieve the goal with the guidance from a self-supervised policy network, which I will introduce later. After the robots, for example, press the dough, the human will also come in to pinch the dough into some like lumpy shape. Then the robot presses twice to flatten again. And then when the human adds some small pieces into the top of the original dough, the robot will still know how to flatten it again. And all similar things also for the rolling. After the robot rolls the dough, the human just constantly goes in and folded the flattened dough into some secret shape or add some small pieces to it. The robot will constantly knows it has to flatten again, so roll it again to have the enough area. Here's what's interesting. After the robots like cut the dough, the humans shows no mercy and destroy everything the robot has just accomplished. The robot knows it has to start from the very beginning and progresses using its original plan in order to accomplish this, in order to make this dumpling skin ready. And after the robot cuts the circle out of it, it will remove the peripheral parts and then using the spatulas to place the dumpling skin onto the dumpling mold. And then it will then place a filling onto the dumpling skin and using the hook to close the dumpling mold in order to make a dumpling. Again, this is still not the levels of performance of how a human can make a dumpling. This is a dumpling with very thick skin and very small dumpling fillings. But this, as you can see, is an extremely challenging task. This is so far the best systems that use a general purpose robot arm equipped with some general purpose tools to make a dumpling out of a robot. So here I'm gonna discuss how this robot cook framework work. And first is at the skill level. That's how does this robot cook decides what specific tool to use at the current stage. Essentially, our robot cook framework will take as inputs the current observation and the final targets as inputs. And then there will be a tool classifier to make a discrete choice about what should be the next tool to use. And in this example, the robot cook selects, for example, the large roller to further flatten the dough to have enough area to cut our circle dumpling skin out of it. And this classifier network is purely self-supervised through the data collected in the real world. And conditioned on the chosen tool, the observation, and again, also the targets, there will also be a policy network determine the precise action to take in a continuous action space. Like again, the tool selection will be the discrete choice to make, and the policy network is making a continuous choice. So it is making like the decisions at both the discrete level and the continuous level. And also after the robot executes the planned action, it will change the dough state. And our systems will close the loop with visual feedback from a depth cameras that we use to observe the state of the dough. And we'll use the updated visual informations to close the perception action loop and plan the next tool to use and the next action to take. And our robot cook not only devises these skill level plans, but also this motion level plans for each skills. And in order to train these models, we're essentially using a self-supervised learning mechanisms. Specifically, based on the tool selected by the tool classification network, we sample the actions randomly within the tool action space. We will then collect the data of some like random DOE initial states in the real world and apply the same actions on these initial states to rule out many DOE trajectories using the learned model. Here is what's the key of this entire framework is still this graph neural dynamics model in the middle. You have already seen this graph neural dynamics model can enable the manipulations of some deformable form as well as the granular pieces. Here you are using exactly the same graph-based neural dynamics model to predict how the shape of the DOE will change if you apply a specific action. And after we have trained this dynamics model, we can essentially regard this dynamics model as some kind of simulator or generator and apply random actions on top of that to generate a lot of data. And then we can use this synthetic data to train our policy network. Essentially, this policy network takes in the current states and the targets, which is actually the predicted, the synthetic generated state using our NERD dynamics model, but the policy network will regard it as the targets. And it will also conditioned on the specific tool, which is the discrete informations that are being inputted to the policy network. And this policy network will output these specific actions. And we are supervising this training process of this policy network by minimizing the distance between the predicted action and the actual randomly generated actions we used to generate this data. And again, this graph-based neural dynamics model is still the center of this framework to allow us to have sufficient data to train this policy network. And our graph-based neural dynamics model specifically will take in the initial states as well as these actions and iteratively predict the future states and future configurations of this DOE when inputted with this action sequence. And here we are showing some specific examples. For example, for this scripting task, our dynamics model will predict the change of the shape of this DOE. And here, the blue points essentially shows the shape of the DOE, and the red points shows like the shape of the tool. The first row is our model's iterative prediction, and second row is the actual ground truth we obtained from the real environment. As you can see, our model's prediction accurately match the ground truth. Here's another example where we have a pressor press down and to deform the DOE shape. And you can see our model also predicted that the shape will be compressed, the shape of the DOE will be compressed after you apply this pressing action. Similar things also is true for the rolling. And here we are showing we are rolling the DOE piece, and our model can also predict that the surface area of the DOE will be enlarged as you apply this specific action, which also nicely matches what's actually happening in the real world, which shows in the second row of the ground truth. And here is our data collection process. And what's interesting about our method is that our approach only requires 20 minutes of random interaction data per tool to learn the dynamics model. This is thanks to the structures we are incorporated into our systems. Because we are using this particle as a representation, we are also using this graph neural network as the model architecture. So the node encoder is shared among all nodes, the edge encoder is shared among all edges. So this kind of structures allows us to have very sample efficient learning process. Like with just 20 minutes of interaction data, we'll be able to learn a very 20 minutes of interaction data per tool to learn a decent dynamics model for this DOE interactions. And our neural dynamics model can also be used to do different other tasks. For example, here the task is to using those tools to deform this DOE shape into some letter shape cookies. Here is to just actually show the process of deforming this DOE into the letter shape of R, O, B, C, and K. When you put them together, you can spell out the name of this project like Robot Cook. Now our collect data is based on a real DOE recipe containing flowers, water, and salt. shown on the first row. And the learned model without any additional training can also generalize to other deformable materials, such as Play-Doh, air-dry clay, as well as modeling foam. Here we also provide quantitative comparisons between our method and the baselines. Our method consumes the least amount of time, shown on the top row in the red box, and it is also achieved significantly higher accuracy as measured by comprehensive human studies, where we ask the humans whether they can recognize the letter shapes that is manipulated by as a result of this manipulation process for the robots. And notably, we compare our work with a baseline that does not learn a policy, but instead directly plan with the learned dynamics model using sampling-based trajectory optimization approach. This method requires much more time and achieve substantially poor performance, indicating the importance of this self-supervised policy learning procedure using the learned dynamics model. We also compare our method with a baseline that uses the state-of-the-art physics-based simulation methods, the material point method, abbreviated as MPM here. What we observe is that even with extensive system identification, the identified MPM simulation is noticeably less accurate than our model, where our model is directly learned from the real data and real interactions. Anyone have any questions?
Any questions? Yeah.
For the human accuracy, is it like a person determines if the task was completed or not? Is that what you're saying? Or what is, I don't understand the human accuracy metric.
The human accuracy here is that we ask the robots to manipulate the dough into different letter shapes. And then we ask the human whether they can recognize this letter. And if they can recognize this letter, we will ask the human subject to classify what letter it actually is. And that is what we mean by human accuracy, the accuracy of recognizing the resulting letter shapes.
Okay, and so then you took all these methods and then asked a collection of people, hey, does this look correct? Is that?
Yes.
Okay.
What letter shapes does it look like? It's A, B, C, D. And like 90% of the time, and the human subject can accurately classify the manipulation results out of our robot cook system.
Okay, cool. Thank you.
I want to ask a question.
Yep.
So what if I wanted to introduce a new tool, like what would need to happen? Would I have to like spend 20 minutes for every new tool? Or would it be configurable?
Yeah, thank you for your question. That's definitely a great question. Currently, as you can see from our visualizations, we assume we know the shape of the tool because we 3D printed the tools. So we can naturally assume we know the general geometry for those tools. And currently we have 15 tools and we learn dynamics model for each and every one of the tools. And it is actually individual models predicting the interaction effect of individual tools. So yes, like if you introduce the new tools, you have to spend another 20 minutes of collecting the interaction data for the model to know the effects of this interaction process. But this is the current design. But I could totally imagine if the model has seen enough variations of the tools, it could naturally incorporate and consider the geometry of these tools and be able to generalize to new tools where the tool has never seen before, because of the use of particle as a representation, which naturally encodes the structure and the geometry for those tools. So to answer your questions briefly, yes, for the current design, if you introduce a new tool, you have to collect new data to train the model. But as the model see more and more tools, I would expect better and better generalizations to unseen tools. Okay, cool.
So you train a graph neural network per individual tool in your framework? So there's no like parameter sharing between the different dynamics models? Is that what you were saying?
Yes, currently for each individual tools, we collect 20 minutes of data and we learn the dynamics model just based on this 20 minutes of data. So if we have, for example, 15 tools, we'll have 15 dynamics models modeling the interactions of those tools. Currently, we don't have any parameter sharing. But as I have said, because we don't believe the generalization capabilities with just 15 tools. We think if you really want to like wide spread generalizations to like arbitrary new tools with arbitrary geometries, you really have to have data that contains the interactions among a wide variety of tools. And when you have that type of data, I believe a shared parameter dynamics model would be able to generalize to like novel tools.
Okay, thanks.
Sounds great. Okay, thanks for the questions. So I will continue. So far, what we have discussed will be the structures that combines the particles and graph neural networks. It allows the dynamics modeling of rigid objects, fluids, and deformable objects. And it also can model the interactions between the object and various of different kind of tools. And because of the neural dynamics model can be used within some self-supervised learning framework, it can also allow us to do long horizon task and motion planning. And because of this structure, there are two key advantages we can obtain. The first advantage would be generalization, where the learned model can generalize to systems that are larger than during training. For example, the fluid examples I showed earlier, where our system can generalize to environments containing 2 times more fluids than during training. And can also generalize to unseen target shapes. For example, the granular piece manipulation examples, where if you manipulate this piece into some target shapes of complicated letter shapes, those kind of letter shapes has never been seen by our dynamics model during training. But because of these structures, our methods can achieve those targets, although it has never seen those targets. So this is the first advantage. The second category of advantage will be sample efficiency. For example, for this DOE manipulation task, although the dynamics of the DOE is complicated and the degrees of freedom of the DOE is extremely high, but we only require 20 minutes of offline interaction data for us to learn a decent dynamics model for each tool. And this thread of work has inspired 2 major threads of follow-up work. The first thread of follow-up work is more on the graphics or intuitive physics domain. That is learning large-scale graph-based dynamics model. Here are some works I particularly like, for them from DeepMind, Intel, and Stanford's on the modeling of large-scale particle systems, intuitive physics, as well as mesh-based systems. The other thread of follow-up work is to use particle as representations for deformable object manipulation. Here I'm also showing some particularly interesting work on manipulating amorphous materials, clothes, elastic materials, as well as this benchmark from CMU on deformable object manipulation. So those are some of the follow-ups work our work is enabled. And let's go back to the slides and look at our problem formulation again. Like earlier, I emphasized the importance of the design of this sim representation Z. But if you have noticed, like some of the early like manipulation results I have shown, although they are tackling complicated tasks and shows very interesting, like from my perspective, very impressive and interesting manipulation results. But the objects we have seen that the robot has been manipulating are still mostly made of homogeneous materials. There are some heterogeneous interactions, for example, the tool and the dough. But typically we assume we know the shape of the tools, and the objects we're actually predicting the dynamics for are typically just homogeneous. But many household tasks actually involve not only just homogeneous materials, that involves the rigid object, deformable object, and their interactions within this kind of task execution process. So what we would like to argue is that we have to think again about the right representation we want to use to describe the environments in order to have good generalization and manipulation process, especially in more complicated household tasks. Let us take this very simple example as an illustration to show why the representations we want to focusing on has to simultaneously satisfy the requirements on the 3D, semantic, and dynamic constraints. For example, here the task is we want to like organize the shoe on the shoe rack. As you can see, during the manipulation process, there are actually a dynamic movement of the shoe, and we actually want to know the dynamics of this kind of interaction process. And also, as you move the shoe from the bottom to the top of the rack, there's actually like a 3D movement. We actually have to understand the 3D structures of the environments in order to do these tasks reliably. And then as you can see, the person are not just move the shoe randomly. They are aligning the shoe, for example, tip to tip or heel to heel. That means the semantic information within this environment is also extremely important to accomplish this shoe rearrangement task. So what we want to argue is that the representation we want to use for general purpose household manipulation tasks has to be simultaneously 3D, semantic, and dynamic. And there has been a lot of progress recently on developing this general purpose visual foundation models like Segment Anything or Dino V2. But a lot of these visual foundation models is typically developed in the computer vision community. And mostly they are just focusing on this 2D image understanding or segmentations or representation learning, which are not particularly suitable for 3D real-world robotic manipulation tasks. So in this work, we propose a DQ field, a representation that's leverage the advances of those foundation models in the computer vision domain and trying to obtain this unified representation that is simultaneously 3D, semantic, and dynamic in order to allow open world generalizations for the manipulation task. And here is how the DQ field is constructed. For example, given these 2D observations, especially multi-view RGBD observations, we'll first use the foundation models, like for example, grounded SAM and Dino V2, to map the input image into some feature volumes W. And this feature volume is essentially some 2D feature descriptions of this 2D image. But we want it to be 3D. So we will project this 2D information into this 3D space. And we are using an implicit field, specifically for any arbitrary 3D points inside this 3D space. We will project these 3D points into this 2D image domain. Then we'll be able to extract the features from this 2D image plane. And these features are derived, again, from those foundation models. We are aggregating those information into this 3D space, which will give us this very natural 3D neural fields describing this environment and powered by those features learned by foundation models. And here is how it actually looks like. For example, for this scene containing 3 shoes, we'll be able to have 3D reconstructions. Here, what we're showing is essentially a mesh reconstructions out of our field representation. And we can also do instance segmentations to obtain some semantic information at the instance level, shown in the second row, this mask fields we're obtaining. And we can also go one level finer by obtaining these descriptor fields that describe the semantic information at an even finer level. Here, what we're essentially showing is that this field model the environments in 3D and also contains semantic information at different levels of abstraction. And here, I want to show some very interesting visualizations of how the fields will actually enable. For example, what you are seeing in this video is that on the left, there's an image, which we will call a reference image. There will be a red point moving on top of this reference image. And on the right, we are showing this 2D image as well as this 3D reconstructions of this 2D image. And this reconstruction is, again, like using Marshall cube to directly extract it from our neural fields. And what we are highlighting here are the corresponding regions, like the heat map within these neural fields that corresponds to the Turing points shown on the top left, these red points. And we overlay this heat map on this 3D mesh visualization, as well as we also project them into this 2D space to make it more clear. And you can see when the point is in the rim area, or the rim will be highlighted. That means it can accurately recognize the very fine-grained semantic informations from this mark. And for example, when the mouse is, for example, within the handle, you can also see on the right image where all the handles has been light up, which nicely shows that we can provide this free category level generalizations because we can have this 3D fused field. And this 3D meshing is also typically very stable because we are fusing information from multiple viewpoints. And here's another examples where on the left is again also the Curie image. On the right is not real image. On the right, what we are showing are actually simulated image. All you can see here is that when we query the points on this 2D plate, it actually recognizes the round plate instead of this this plate with non-circular shape. You can see when you query a specific point on this plate, you also be able to see like it is able to capture and nicely capture the symmetry information of this plate and give you like a circular activation pattern. And this third example, I think, is particularly interesting. For example, when the query point is in the head of this fork, you can see on the right, the feature fields also highlights the head of this fork. But as soon as this point is moved to the bar of this fork, you can see the bar, not only the bar of the fork has been highlighted, the bar of other utensils has also been highlighted, which shows some very fine-grained understanding about the semantic informations within this kind of environment. The same is true if you also query, for example, the knife. For example, if your query point is at the bar of the knife, all the bars has been highlighted. But as soon as this point is moved to the head of this knife, only the knife areas on the right side images has been highlighted. That shows very interesting semantic understanding about the utensils within this environment, which could potentially power a lot of like downstream applications that we could imagine, like for example, functional use or have some spatial specific correspondence between instances of different instances within the same category. And here, because we can nicely have this kind of correspondence, so we can also track the points over the 3D space and allows us to build this kind of dynamic representations of the state changes of the environment. Here we are showing two examples where we are moving shoe around or like lift the shoe up and place it down. We can nicely track the movement of the shoe in the 3D space. And here is how our representation can be 3D, semantic, and dynamic. And then we want to use these representations for some downstream manipulation task. And in order to do these manipulation tasks, typically what we are doing is to specify a Go image. For example, given this Go image, we will again using our the foundation models to map it into this descriptor map. And then we will have our field representations of the actual environments. And we can then, using some kind of correspondence matching algorithms to find correspondences between our current environment and the Go image. And then we can define the planning cost by measuring how far how well our configuration matches our Go image. And one interesting thing you can see from this Go image is that this is not an image. This is also not an image from a physics-based simulator. This is actually an AI-generated image. But you can still nicely find this nice correspondence between the real thing and this AI-generated image. And to show the generalization capability of our systems, we evaluate our systems on a wide range of real-world objects, including shoes, mugs, utensils, as well as fruits. And on the right are some of the example images we use to specify targets. And the target image are like 2D sketches, AI-generated image, real images, but real images with different set of instances, as well as images from different type of viewpoints to, for example, this mug one. And here is how the planning process works. For example, after we have this Go image, as well as the correspondence of that Go image with our real thing, we'll be able to rearrange this environment to match our Go configuration. And then we are also showing that our systems can generalize to different kind of instances. For example, on the horizontal axis, this x-axis, we're showing instance level generalization, where there's the same Go image, you could also manipulate like instances, different instances to achieve the same Go configurations. And when, for example, the fork and the spoon are reversed, we can also nicely recognize their differences. And also when the image is rotated, we can also nicely recognize the difference and find the correct match to achieve the target's configuration. And also we have shown like, it doesn't matter whether you're in simulation or in the real world. For example, if your Go image is in the real world, we can also organize the shoe in the simulation using a mobile manipulator. Here's another example where the Go image is like a AI generated image. You can also place a corresponding fruit and food into the plate that correspond to the target configuration. Here, the Go image is a real image. You can also allow these robots to organize those marks in the simulations. And here's another example of making the table.
Just a quick question.
Yes.
I'm just curious to know if it can reliably tell the left shoe from the right shoe apart, because they would have like very similar high-level semantics, but like a subtle difference in shape. So how does that work?
That is a very good point, and this is actually one thing we observe in the real environments. It's actually a bit hard to distinguish perhaps between the left shoe and the right shoe. There are shoes where it's kind of asymmetrical from the left side and right side, so that's easier to distinguish the left shoe from the right shoe. But when it's very, very similar, it's actually very, very hard. And actually, if you look at this simulated video, if you zoom in, you realize this, for example, these two shoes, they're both right shoes. This is also like limitations of this simulator. This simulator only contains assets of the right shoe. It doesn't have the left shoe. So we place two right shoes there. So this also is an indication that currently we cannot distinguish the left shoe from the right shoe very, very well. But it has to focus on more fine-grained geometries of the shoe. And I think that requires some further investigations on how to incorporate more precise geometric information in the pipeline.
Thanks.
Yeah. And here are just some other more examples where because we have tracking information, we can build a dynamics model on top of that. And this dynamics model can allow us, for example, to organize the granular pieces where we want all the pieces to just go to one place, or for example, to reorient these shoes into achieve the target configurations, where our 3D fields can allow us to do some more fine-grained poking or touchings to have it better aligned with the target configurations. And the take-home message for this work would be, we are using a structured representation. A structured representation is simultaneously 3D, semantic, and dynamic. It allows zero-shot generalizations across instances and environments. And it also, the ability that's generalized across instances and environments is powered by the advances in the visual foundation models. And with more and more powerful foundation models, they can very nicely integrate it into our neural fields in order to enable the robots with even better capabilities. And our systems allows very flexible goal specifications. Like we can specify the goal in image in the simulation in the real world, and we can have instance level variations or have different kind of context variations. Or even if your goal image is AI generated, it doesn't matter. Our methods will be able to recognize the semantic correspondence and successfully accomplish this task. So I have one additional work, but I don't think I have sufficient time. Currently, what I've discussed would be the selections of the scene representations. I have another work that's trying to really thinking about what kind of cost functions we should be using in order to do various of different kind of manipulation tasks. I will just show the motivation and some highlight of this work, and is that what is the task definitions in the context of home robots. For example, defining the tasks and write down the objective function for those tasks can actually not be as straightforward. For example, in self-driving or drones, specifying the task can be straightforward. You just tell the robot where the destination is. But what does it mean to fold the clothes? What does it mean to make the table? So there's a lot of common sense informations that are underneath the simple sentence, make the table. So that's why we are using foundation models, that's foundational vision models and foundational language models to command the robots to do all different kind of like manipulation tasks in the open world, where the task is specified in the natural language, like tear open the vitamin bottle, measure the weight of an apple. I won't go into the detail of this, but this I think is a very interesting work, and I highly encourage to check it out. So just to summarize what I have discussed, essentially what I have discussed is what kind of representation I want to use to describe the environments. I've shown, for example, the advantages and limitations of the particle-based representations, which itself is extremely powerful for manipulating, for example, objects made with homogeneous materials. We have shown some surprisingly challenging tasks like manipulating dumplings, and our system can successfully accomplish those tasks. We have also shown in order to generalize those capabilities into more open world and more diverse real world environments, we actually have to extend our representations to ask it to be not only be 3D, but also be semantic and dynamic, where the semantic can be describing the environment at different kind of semantic levels, like the instance level as well as a part level, to satisfy our requirements for real world object manipulation. So in the end, I want to thank all my collaborators. Without them, it would be impossible to do all the works I have shown before. And I'm happy to take any questions now.
Awesome. Thank you so much, Yunzhu. Yes, maybe one question on the first part of this presentation. Mm-hmm. I sometimes wonder like how much physics you need in your policy. So the example I have for this is I can reliably pour a glass of water without having a very good understanding of fluid dynamics, right? I only have a very rough understanding of fluid dynamics. So I'd like to hear your thoughts, like how much physics do you think we'll need in like the future robot policies?
That is a very good question. I've been thinking about that questions for a few years, and I can give you some interesting examples, like the modeling of the environments as well as the policy of the environments. Sometimes the modeling of the environment can be very simple, where the policy can be extremely complicated, like the example of Go, where the dynamics of the Go board is just very simple, just a rule of the game. But in order to learn a good policy on top of this Go board, it can be extremely complicated. On the other hand, like the examples you have been, you brought up, like pouring fluid, the dynamics of a fluid itself can be complicated. It's fluid dynamics. But the policy for actually doing this task can be surprisingly simple. You just, for example, making sure like the rim of your cup is aligned with some containers, and then you are making sure the fluid is going out of this cup into the container. So how much we should model the dynamics is actually an interesting question in this context. Sometimes, for example, for the granular pieces, we have to have some more detailed like dynamics model to describe this detailed geometry. But for the fluid pouring example, we do not need a very detailed dynamics model to describe the detailed dynamics for this fluid. So that's why I think intuitive physics in this context is an important concept to bring in. Like we have to really think about what kind of intuitive models we humans have for doing those tasks. And these intuitive models can be extremely inspiring for how we should design the systems for the robots. Because we humans have this intuitive model, we just predict whatever happens if we apply a specific action. This predictive capability is not particularly accurate. For example, if I'm pushing my phone forwards, after I apply this push, what specific angle this object will rotate, we humans don't know. We humans cannot make very precise predictions. The similar things for the fluid, like what about this drop of water? How far will it go? Like what direction will it go? We cannot predict them. But most often we don't have to predict them. So really thinking about like how accurate and how diverse our human's intuitive model is can really inspire us how much physics we should have and how much modeling we should have for our everyday environments. So that's why a lot of tasks I've been doing, like the deformable form, the dumpling ones, are also some of the tasks we humans enjoy. That's why I choose those tasks to show the power of intuitive physics for the everyday manipulation tasks.
Great, thank you. That was a great answer. Other questions?
I guess I just had one question about for the 3D reconstruction stuff you guys did. Did you do any experiments? So maybe I just misunderstood, or this is just not my area of expertise, but you had two cameras and you're doing this correspondence between them. And I was just curious, like if you guys did any experiments about like moving the camera slightly after you trained it. So like if you perturb the angle, does that affect the performance of the 3D reconstruction at all?
That's a good question. Yeah. Actually, although here we just showed two cameras, but in our actual experiments, we used 4 cameras to observe the environment to obtain as complete of a geometry as possible. And it's totally okay to change the pose of the camera as long as you recalibrate the camera, because this system doesn't require any training at all. We directly use foundation model, so everything is 0 shot. We are not training anything. So even if you change the pose of the camera, as long as you recalibrate the camera and can still fuse the information into these fields, and we are okay. And that actually provides some like different. Imagine you have a wrist mounted cameras, or you add an additional cameras that provide you with better view of these environments. Those information can be very naturally incorporated into our current representation.
So I guess then, like, what exactly is this thing you're doing the correspondence of? Is it like the deep feature representations? Because I mean, I could imagine you could just take the raw pictures and be like, okay, these are the corresponding things or something. So like, what exactly is the D3 fields adding that we couldn't do without just, you know, calibrate the cameras and say these points correspond to this or something manual, I guess?
Like there are several key advantages. First, because the fusing process is essentially distilling the information from this 2D image into this 3D field space. So that provides consistency. Like, although these foundation models that provides some nice features that can potentially give you correspondence, but if you change the viewpoints, those features actually will have some changes. But as you distill those information into the 3D space, it becomes consistent, meaning even if, for example, we are rotating this field, the field doesn't change at all. It is viewpoint consistent. So that is one thing. And second thing, because like this representation is 3D, we naturally know the 3D coordinates of those semantically meaningful part. So that means if you want to do a specific task, like moving the end effector to a specific locations that associated with the query features, you can go there. So this allows some 3D space manipulation. And the third thing would be, after you fuse this information into this 3D space, what you could enable would be this kind of tracking informations. You're tracking the information in the 3D. And this 3D also provides you the structured constraints. For example, if you know this is a rigid object, those constraints can be very easily incorporated into the 3D space. But enforcing rigidness constraint on the 2D image is just not as intuitive.
Okay. Wait, so does that mean like D3 is like you take an image and it projects, I predict this is the 3D shape of the world from this particular perspective? I guess, is that what it's actually doing, or?
Essentially, just like you have multi-view information, we are just project those 2D information from this multi-view observations into this 3D space, and what we're getting is this 3D field.
Okay. I think I just need to look up on Dino then, but thank you.
Yeah, thanks so much, Yunzhu. I think we'll leave it at that. Thanks again for the talk, and yeah, hope to see you around.
Yeah, thanks again. I appreciate the invitation, and also appreciate all the questions. It was very insightful. Thank you so much.
Okay.